All right. I'm sorry I'm not able to be with you today, um, but we're going to go through a bunch of examples of how to use um, or how to solve problems with acceleration, starting with kind of where we picked off last class. So just as a reminder, we have three main equations oops, there that we are going to use when there's acceleration involved, right? So it's v final equals v initial plus at. Change in x equals v initial times time plus 1/2 at squared, and v final squared equals v initial squared plus 2a change in x. All right, and again, our three kind of step process for this is going to be identify the variables. All right, that's 1, 2, pick equation, and 3, solve. Okay, so that's our plan for these problems here. There are going to be a few wrinkles as we keep going along, but that's the idea. So um, our first example is going to be this one. Okay, this is most similar to what you guys saw on Wednesday. Um, so we'll run through it really quickly. We have 3 meters from the base, so that means they are going to have a displacement of 3, a deceleration of 8, which means it's going to be negative, opposite the way they're going. And the third variable we have is the final velocity is 0. If you're sliding into a base, and you're coming to a stop, as it shows here, that means the v final is going to be 0. How long did it take? So we're trying to find time. Now, if you're sitting there, at this point, we've got our first step done. Our second step is to pick an equation. All right, I paused for a second there, hoping you would recognize that there's a little bit of a weird thing going on here. These three variables together and t, the three known ones in the t, do not fit in a single equation together. And that's fine. We can just use two equations instead. So we've got change in x, a, and vf. I can't find t directly, so I'm going to go ahead and find v initial. Okay, the initial velocity. So I can do that with v final squared, v initial squared, plus 2a change in x. Okay, that gives me 0 equals the initial squared plus 2, negative 8, 3, which is v initial squared minus 48, which means that v initial equals the square root of 48, which is just about 6.93 meters per second. Now that I have that, I have v initial, change in x, a, and vf. I can use any of the equations with t in them to find t. Probably the easiest is v final equals v initial plus at. 0 equals 6.93 minus 8 times t. T is going to equal 0.8, oops, 0.866, 0.866, as you guys like to say. Okay, and that's our answer. Okay, so this is on top of the first the problems we did on Wednesday. This is the first one we had where it required two equations to solve. Now we're going to step up the difficulty a little bit. So I'm going to let you guys read this problem for a second here, and then see if you can identify what's interesting about this problem. Okay, so hopefully you guys recognize that what's interesting about this problem is that it's got two different parts to it. There's the part where it's going faster, accelerating, and there's a part where it's decelerating. And just like the problems we did previously with two different average velocities, if we have a problem with two different accelerations, we have into parts. I told you that was going to come back, and it definitely does here. Yeah. So, part one. Okay, what do we know about that? Starts at rest, so v initial equals 0. It has an acceleration of 6, and t equals 4. Okay. Part 2 has it's decelerating, okay? And wow, I don't know very much here. I guess I just know that it's going to come to a stop, so v final equals 0. That's all I know. It's nowhere near enough. And then I guess for the overall part, I just know that the displacement is 75. Okay. You actually also know the v initial and v final of this are 0 of the overall, but you can't use no equations for this because all of the equations require just one acceleration, and for the overall we actually have two different accelerations, so we can't actually use this. We can't do any equations with this, but it's still important to know that this is 75 meters. Okay. All right, so let's look at part one. That's where we got the most information, so that's the best place to start. We got three variables. We can go ahead and find v final, which is going to be 0 plus 6 times 4, because we're using the first of those equations, 24. Okay, and then we can use any of the other equations to find displacement. So let's go ahead and use change in x equals the initial times time plus 1/2 at squared. Okay, we get 1/2 times 6 times 4 squared. That's equal to 48 meters. Okay, now neither of these answers the question we're asking. Like, what was the deceleration while braking? I'm trying to find this acceleration over here. Okay, but they're both vital to find in order to do that. They don't directly help us. They're one step away. Okay, the first one here, displacement might be easier to see. If the first part went 48 meters, we can figure out how far the second part went. The first part's 48, the overall is 75. This change in x is going to be, displacement is going to be 75 minus 48, or 27 meters. Okay. The second thing here is we actually know what initial velocity is here. Okay. The initial velocity of part two, like part two starts right after part one ends. So whatever's happening at the end of part one becomes the beginning of part two. This is actually a really important thing that's going to show up a bunch. We're going to come back to it several times over the course of the year. But this velocity, this final velocity here, becomes the initial velocity here. And now we have three variables. So I can find acceleration doing v final squared equals v initial squared plus 2a times the displacement. 0 equals 24 squared plus 2a times 27. That means that I get 24 squared equals negative 2 times 27 times a, and we do that, a ends up being negative 10.67. Okay. All right. Let's look at another example. We got three more examples to run through here. Okay. This is another one of these ones where it's got different parts. We've got a train with maximum acceleration, deceleration, 2 meters per second, and a maximum speed of 20 meters per second. Okay. This one is a little bit tricky to think of, but you can actually sort of guess what's going to happen here. It makes it a little bit easier. So what happens when you're on a train between stops? You speed up, you then go at a nice little normal speed or a nice little maximum speed, and then you slow down again. Okay, so we actually want to break this up into 3 parts this time. 1, part 2, part 3, and we'll even look at the overall here. Yeah. Okay, so we think about what we know about each of these parts. Part 1, acceleration is 2, initial velocity is 0, and then final velocity, this is the part where it's speeding up, maybe we should say that, speed up. And the final velocity, the maximum speed, is going to be 20. Part 2, this is max speed, okay? Part 3 is slow down. Okay, as we learned last question, at the end of the first part, this final velocity here becomes the initial velocity here. And then because it's maximum speed, it's not slowing down or speeding up, so our acceleration is 0. Our final velocity is also going to be 20. Okay? And then for part 3, it starts that when this is when it like has to start slowing down, so its initial velocity will be its maximum. Its acceleration will be -2, right? Because that's the maximum deceleration. And then the final velocity will be 0. Go ahead and solve for everything we can from part 1. All right, you might be tempted to start with any of these parts, and you can start with 1 or 3. Oh, I forgot to write. What do we know for overall? Overall equals 500 meters. Okay. All right, so in this first problem here, 2, 0, and 20, we were looking for, let's go ahead and find time. Okay, so I should find both of them. To find time, V final equals V initial plus AT. We got 20 equals 0 plus 2 times T. T equals 10. And then for displacement, change x equals V initial times time plus 1/2 AT squared. And we will get that displacement is equal to 1/2 times 2 times, this is 10 squared, and this ends up being just 100. Okay. Ideally now we would do part 2. We've got 3 variables here, but they're actually a weird combination of variables. You actually can't solve for anything else. So we actually have to skip part 2 here. If you tried, you would just not be able to solve for anything. But we're going to skip 2 and go to part 3. And it turns out if you solve part 3, you get a lot of numbers that work out exactly the same way you did for part 1. Turns out that time is 10 and change in x is 100. You can show that, but the equations look really the same because all we switched is initial velocity and final velocity. Okay. With this information, if I know the first part is 100, the third part's 100, and the overall is 500, I get that the change in x here is 300. All right, and now I can solve for the time because it's going to be change in x equals v initial times time plus 1/2 AT squared. That part is 0. So I get that 300 equals 20t, t equals 15, and I end up getting that a total of the total time equals 10 plus 15 plus 10, 35. Oh, not meters per second. That's incorrect. Just seconds. Okay, I'm going to ask the sub to pause the video here, and for you guys to go ahead and look at your homework assignment here, and on WebAssign, and do a couple of problems. Maybe like give you like 10, 15 minutes to do a couple of problems here of this type. Okay, you'll see this would be problems 4, 5, and 6 are this type. Yeah, 4, 5, and 6. Okay, so pause this about 15 minutes, please, and you guys can work on problems 4, 5, and 6. One of them you'll see is pretty familiar, so have a chance to do it. Okay, we're back in action. This is another sort of additional step we can thing we can do with these kinematics equations. Okay, so take a moment and read this problem and see what's interesting about it compared to the previous problems you've done in this unit. Okay, hopefully you noticed here that there's two objects. Okay, so unlike the last couple problems where there was multiple parts with the same object, this time there's just multiple objects. So let's look at what happens there. Again, we want to treat everything kind of separately here. So let's go ahead and say, okay, what about I'll do the dog, then we'll do the squirrel. Okay, and then we'll look at the combination of them. What's true, what's got to be true about both of them. And that's the interesting part. These two parts right here, hopefully, relatively straightforward. So dog accelerates at 4 meters per second squared. So it's 4. Okay. Starts from rest. So V initial equals 0. And for the squirrel, it goes at a constant 10 meters per second. That means that V initial is 10 and acceleration equals 0. Now notice, I'm ignoring this starts from rest 5 meters. I'm ignoring like the fact that the dog starts somewhere else. That's not a dog thing. It's not a squirrel thing. That's a both thing. We'll do that in a minute here, right? Now, you might be like, okay, Aiden, you told me something the other day. You told me you need 3 variables to find a fourth. I've only got 2 for each of them. Why don't we just we can just give up now? No, we can't do that. This is solvable here. Okay. So we're going to do something here that's not necessary for this problem, but it will be for other ones. So we're kind of doing, let's say the dog's time is just the time for the dog. Okay, and the squirrel's time is the time for the squirrel. And let's pretend we know these numbers. If I was trying to find displacement for the dog or displacement for the squirrel, and I knew initial velocity, acceleration, and time, hopefully you can guess what equation I would use. Ideally, it would be V initial times time plus 1/2 AT squared. All right, and I would get that change in X for the dog is equal to 0 time of dog plus 1/2 times 4 times time of dog squared. Here it would be 10 times time of squirrel plus 1/2 times 0 times time of squirrel squared. Simplify both of those and you get that displacement of the dog is equal to 1/2 I don't know why I'm doing that. We can simplify that. 1/2 times 4, we all know that one is 2t dog squared. Here it is equal to 10t squirrel. Okay, still can't solve either of these, but that's all right because now we consider the both. Okay, what is happening here? What does it mean for a dog to catch a squirrel? Well, might help for us to draw this, and I am not good at drawing squirrels or dogs, so I'm just gonna use S for the squirrel and D for the dog. Okay, the squirrel runs to the right and the dog runs to the right. Okay, and this is change next to the dog. This is change next to the squirrel. And the final thing we were told is this distance is 5 meters. So if we look at this, all of a sudden we know, hey, the dog goes the same distance the squirrel goes plus 5. So change next to the dog equals change next of the squirrel plus 5. Okay, so I get 2 dog squared plus 10 times of the squirrel squared. Okay, plus 5. Now, the last thing we have to do here is think about the time. In this case, is there any thing that says the dog started before the squirrel or the squirrel started before the dog? Yes, the squirrel's already moving, but based on what the information we got, the dog starts moving right at the time, the squirrel starts moving right at the time. So these two t's are actually the same. Okay, so we get that t of the dog equals t of the squirrel. Okay, and now we can solve for this t. 2t squared equals 10t plus 5. And ultimately we can do the Pythagorean theorem. Not the Pythagorean theorem, sorry. What's it called? Quadratic formula. Quadratic formula with this, or you can be lazy and ask your computer to solve it. Whatever. Not too big a deal. You get the time is equal to 5.46 seconds. Once you have that time, you might recognize, okay, so, all right, I didn't even think about what the question was asking here or talk about when we started. That's okay. How fast is the dog moving when it catches the squirrel? It turns out you have to solve for this before you can do that. Okay, you don't have a choice. All right. So once we have that time, this is what you should generally solve for on these problems always first is this time. We can go and find the speed of the dog. Because the speed of the dog, right, once we have the time, is just v final equals v initial plus at, which is 0 plus 4 times 5.46, which is 21.8 meters per second. Okay. All right, that's a pretty challenging problem. This is about as hard as a problem can get. I'm going to do another example that's really similar to it, just because I want to really hammer home how to do this because these problems are challenging. All right. All right, again, we have a similar example. We have a dog. We have you. And we could again say both. The dog has an v initial of 0, an acceleration of 1.5, and a time, again, we'll do of t of the dog. U, initial velocity of 1, acceleration of 0 because it's constant velocity, and t of u. So we can do the same thing. Change in x of the dog is equal to 0t dog plus 1/2 times 1.5 t dog squared, or 0.75 t dog squared. All right, same thing with us. Zero times tu squared, and we just get 1 times, or actually we don't need to do that. Okay. All right, both. This time we've got a little dog here. We've got you here, and the dog is coming towards you, and you're coming towards the dog. Okay, so it's not like one of these is equal to the other one in any way, shape, or form, but what's true, if this is 20 meters, what's true about the displacement of the dog and the displacement of you combined? Well, change in x of the dog plus change in x of you is equal to 20. So I've got 0.75 times the dog squared plus time for u equals 20. Okay, again, we don't have a head start really. We don't have a time difference. It's not like I said, like the dog is delayed by 3 seconds or anything like that. So these two times are the same. Okay, it's just good practice to treat them as different up until now. And we have 0.75 t squared plus time for u, or t, just t, equals 20. And again, we can use the quadratic formula. I get 0.75 t squared plus t minus 20, 0. Quadratic formula, or you can use an online calculator of some sort. If you do this, you should get that t equals 4.54 seconds. Okay. Yeah. So we got to this point here. I am looking at now at asking you guys to try number 10 or number 11 on the WebAssign here. Okay. All right. Those are the closest to these two problems. Okay. They're worth a try. All right. Good luck. We have not talked about acceleration graphs. Or velocity versus time graphs. So those three problems, which are 7 and 8, we're going to have to just, we'll come back to those on next week when I am back. Last thing to note here on the homework, so that means the homework is going to get pushed back a little bit, although I hope you will try and do all the other problems except for 7 and 8. The other thing you'll notice is that the last few homework problems, the last 6, 12, 13, 14, 15, 16, and 17, they're all worth 0 points. That's intentional. Okay, those are sort of optional extra practice problems, not required to do them. You can try and do one, you can try and do like the ones that like, oh, I kind of don't get this kind of problem, maybe I want an extra one of those. Or you can decide to save them for like solving when we have a test as review. Up to you, but they're entirely up to you. They don't count for anything. 11, 12 through the last 6, 12 through 17, worth 0 points. Entirely up to you about whether you want to do them, whether they'll be helpful. Okay, I will have a good weekend. I will see you next week.